this lecture we discuss about critical phenomena, critical constants of a gas. Critical phenomena and critical constants. The critical phenomena and critical constants is what we are going to discuss now. This critical state is something related to liquefaction of gases. A gas can be converted into a liquid by different methods like increase in pressure or decrease in temperature, right. Now, this pressure, what pressure is required at the given temperature so that a gas can be converted into a liquid, what pressure is to be applied, or at a given pressure what temperature to which the gas should be lowered so that it will be converted into a liquid. These are the two ways. Of course, in both the cases the volume is expected to be constant, or with change in pressure or temperature how the volume is going to change. This is all that we have to discuss now. So, this critical state is related to critical state of a gas. Critical state of a gas is a particular set of conditions of PVT, in which a gas can be converted into a liquid and beyond which it is not possible to convert a gas into a liquid. Means, as I told, for a gas to convert into a liquid, first of all, this is gas to liquid. The favorable conditions are, this is a exothermic reaction and decrease in number of moles. Number of moles decreasing and delta H is negative. Therefore, favorable conditions are for a conversion of gas to a liquid is increase in pressure and decrease in temperature. These are the favorable conditions. Now, critical state. So, if once you set up a particular temperature and pressure conditions, further above which if you increase the temperature, even after whatever the pressure to which it is lowered, or to whatever extent the pressure is lowered, still the gas cannot be converted into a liquid. So, basically the point is, upon increasing the temperature, therefore here what happens is, upon increasing the temperature to certain high temperature, then if pressure is increased to any higher value, a gas may not be liquefied. So, what I mean to say is, take a gas in a vessel, in a closed vessel. You have a piston. Gas, and here this is temperature. Now, on increasing temperature, kinetic energy increases. At certain high temperature, where Ke is maximum, then whatever P is increased at high kinetic energy, it is not possible for gas to convert into liquid. So, what we are doing is, you have increased the temperature to a very high extent. As a result, the kinetic energy of the gas molecules is increased very high. Then you increase the pressure. After reaching certain maximum value, increase the pressure. Normally, increase in pressure should favor the liquid formation. That is what here we wrote, favorable conditions, high pressure and low temperature. But here the temperature is high. So, then at a very high temperature, to whatever extent the pressure is increased, the piston you lower it, that is increase in pressure, still the gas will not be liquefied. So, that particular temperature, that maximum temperature beyond which a gas cannot be liquefied at whatever high temperature it is, that is whatever high pressure it is, that is what is called critical temperature. We represent it with the symbol Tc. Similarly, the pressure exerted by a gas at the critical temperature is what is called critical pressure. Of course, the volume of a gas at its critical temperature and pressure conditions is critical volume. Critical state. So, as we have discussed, the critical state is where the set of conditions where a gas cannot be converted into a liquid beyond that particular set of conditions, right. So, this to explain, we take one example, that is the variation of temperature and pressure, the isotherms, the Andrews isotherms, if we take for PV for carbon dioxide, by taking the pressure volume variations with respect to carbon dioxide gas at different temperatures, that is isotherms. If we look into it, then what is actually critical temperature, what happens there, this we can understand. This explanation for this is given by Andrews. So, we call them as Andrews isotherms. Andrews isotherm for carbon dioxide gas. The graph is we draw it at the pressure volume graph at constant temperature, that is isotherm when we draw for carbon dioxide. First, it is observed that at very low temperature, the graph is found to be like this. Okay. This is at very low temperature, this is at a temperature T1 Kelvin. Then at a higher temperature, when the graph is drawn, it is found that the graph is something like this. the graph observed is something like this. This is at T2 Kelvin. Then at another higher temperature, the graph is something like this. Okay. Then this is at temperature of T3 Kelvin. Then after this, the curve is like this. This is T4 Kelvin. Now, these temperatures are of the order of T1 less than T2 less than T3 less than T4. This T1 is actually is something drawn at about minus 13.8 Kelvin, and this is slightly at higher temperature, then this is at high temperature, and this is at about 50.2 Kelvin. So, in the range of 13.8 and 50.2 Kelvin, and the different curves are observed. 4 curves here we have given. At each, here we can draw many curves in this range of different temperatures. For our discussion, we took 4 such curves. Now, in the first curve, if you look at it, the different points, like if you note it down, A, B, C, D. A to B, B to C, C to D. The variations, if you look at it, with the increase in pressure at this low temperature at T1 Kelvin, at T1 Kelvin, which is a very low temperature. At very low temperature, what happens is A to B volume is decreasing, decreasing with increase in pressure. In the curve 1, that is at T1 Kelvin, A to B point, if you look at it, with increase in pressure, from say P1 to or PA to PB, that when you do it, when the pressure is increased, there is a decrease in volume from VA to VB. So, between A to B, short range of pressure, in a short range of pressure, Boyle's law is followed. Boyle's law is followed. That means, between A to B, it behaves as a gas. From A to B, the curve, if you look at it, it is looking like the isotherm that is drawn with respect to Boyle's law. So, between A to B, the gas follows between the pressure of in this pressure range, gas follows Boyle's law. Now, B to C, if you look at it, B to C, when you look at it, volume decreased very high for almost no change in P. Volume is very much decreased from here to here. Volume is decreased very high with almost no change in the pressure. What does it mean? High decrease in volume indicates the gas changed to liquid state. So, this is here B to C, change of state from gas to liquid. Here it is gas, here gas to liquid, right. Now, C to D what? No change in volume, C to D, no change in volume or almost negligible change for any high pressure. Whatever may be the high pressure you are applying, there is no change in volume. That means, C to D, it represents liquid state. So, the C to D, it is liquid state. This is what we. So, between A to B it is behaving as a gas, B to C gas is converting into liquid, C to D it remains in the liquid state to whatever high pressure the liquid is subjected to, right. Now, when you go to the next higher case T2 Kelvin, similar here in this is if you take A dash, B dash, C dash, D dash. If you look at it, here A dash to B dash is the gas range, gas to liquid, this is liquid. So, at increased temperature, its gaseous nature is increased, liquid nature is decreased, or the other way around is with increase in temperature relatively to a high pressure, relatively at a high pressure the gas is converting into a liquid, right. So, here the gas, the pressure range at which it exists as gas is increased. That is what the inference A dash to B dash range is more than A to B. That means gas is existing, gas is not converting into a liquid to a higher pressure range at high temperature compared to that at low temperature. Now, go to the third case T3, where this is A double dash almost B double dash, C double dash, D double dash. Hardly you will find any change in slope overall between C double dash and B double dash, or rather the other way around, A double dash to C double dash, even though we noted down B double dash in between, but actually if you look at it, the slope is continuously changing. Here no change in slope for a large volume gap, here that range is reduced, slope is continuously, almost continuously changing, that with a small interval, with a slight change, slight difference, and of course then this is the almost it is continuously, not just even A double dash to C double dash, A double dash to D double dash, the change in slope is much different and it is continuous. When you go to T4, you do not find any situation where a gas is converted into a liquid, because here you have only continuous decrease in volume with increase in pressure. This is only 2 points that you have to note down, that initial and final, in between you do not have any jumps or you do not have any deviation, large deviation of slopes like in this case is what we observed for the curves. This is appearing as in the whole range of T4, in the whole range of pressure volume at this T4 at 50.2 Kelvin, it is remaining as gas, it is remaining as gas only, liquid is not appeared at all. At T4 in whole range of pressure, it follows Boyle's law. Means it is not converted into a liquid. So, this is the optimum temperature. T3 is the optimum temperature at which a gas can be converted into liquid at certain pressure. Beyond T3, it is not possible for a gas, that is carbon dioxide, to convert into liquid at any pressure. Whatever high pressure that you apply, but gas is not converting into a liquid. So, beyond T3, what is the value of T3? 30.2 degree Celsius. 30.2 degree Celsius, these are not Kelvin, this is degree Celsius. Degree Celsius it is not Kelvin. 50.2 degree Celsius minus 13.8 degree Celsius. T3 Kelvin, this is 30.2 degree Celsius. Beyond 30.2 degree Celsius, 30 or 31.2 degree Celsius, between 30-31, not exactly, but it is somewhere between 30-31. Beyond that temperature, whatever high pressure that you apply, carbon dioxide cannot be converted into liquid. So, for carbon dioxide, Tc is equal to 30.2 or 31.2 degree Celsius. That is the range at which, that is the temperature at which carbon dioxide cannot be converted into a liquid to whatever high pressure that it is applied. This is what all inferences, first of all, in understanding these graphs, from which we can determine the, what do you call, the critical temperature for carbon dioxide. Similar to this, we can determine the critical temperature for any gas by drawing the isotherms. Okay. Then, how mathematically for a given gas we can determine the critical constants, that we see next. So, critical constants for a gas. First, it is critical temperature Tc. By using the van der Waals constants A and B, depending on their deviations, the critical constants for all different gases have been determined. From that, a generalized formula to determine the critical constants of critical temperature, critical pressure and critical volume were given. First, let us see about this critical temperature. Just now we discussed that for carbon dioxide the critical temperature is about 31.2 Kelvin, right. How do we get it? That is, of course, practically by drawing the isotherms, Andrews isotherms at different temperatures. Theoretically, to calculate, the formula given on the basis of the van der Waals equation and van der Waals constants is that Tc is equal to 8A by 27 Rb. 8A by 27 Rb is the critical temperature. That means, if a gas is having the van der Waals constants A and B with certain values, from this if you calculate, then you will get the temperature beyond which a gas cannot be liquefied to whatever high pressure it is subjected to, right. So, critical temperature, again I am repeating that it is a temperature beyond which a gas cannot be liquefied to whatever high pressure it is subjected to, that we determine by using this formula. Then what is critical pressure? Critical pressure is obviously critical pressure easily we can define as that critical pressure is nothing but pressure exerted by a gas at its critical temperature. The critical pressure is Pc is equal to A by 27 B square. A by 27 B square. This is the formula. Of course, for all this formula are derived formulae. right. Pc is equal to A by 27 B square, and critical volume it is volume occupied by a gas at its critical state, that is critical temperature and critical pressure. This V c is equal to 3B. Therefore, at a critical state, compressibility factor Z, at a critical state, compressibility factor Z for any gas, you can get it as ZC, that is compressibility factor at critical state. Compressibility factor at critical state if you take, which is equal to now PCVC by RTC, which is equal to pressure is, critical pressure is A by 27 B square, critical volume is 3B, critical volume is 3B by critical temperature is 8 A by 27 RB, and R is this. So, this if you look at it, right, so in total it remains with 3 by 8. That means at a critical state compressibility factor is less than 1, it is less than 3 by 8, means at a critical state any gas will exhibit what? Negative deviation, that is what it gives, right. Now, but for many of the gases, of course, this is one drawback of van der Waals equation. From this, for every gas it is supposed to be PCVC by RTC is supposed to be equal to 3 by 8 exactly, but for none of the gases it is exactly 3 by 8, it is having a certain range, that is in fact one of the drawbacks of the van der Waals equation. And in addition also we have another drawback for the van der Waals equation, that A and B are constants for a gas, but A and B are not constants for a gas at all temperatures. Only at with change in temperature A and B also are changing for same gas. In fact, because of that reason this is also not exactly coming out to be 3 by 8, because for all the gases critical temperature, critical volume are not same, at different temperatures they will vary. So, is the reason that A and B also will vary from one temperature to the other temperature, and that is the reason compressibility factor at critical state also is varying, right. So, but anyhow, theoretically to say this is the compressibility factor for any gas at critical state. Now, after this also what we have to look it into is a little more detail, small applications or behavior of the gases to understand inversion temperature and Boyle's temperature. These are the other two terms we should know, and what is inversion temperature, and of course there also it requires to know about the little about Joule-Thomson effect, that we will discuss now. So, now just we see what is inversion temperature. Inversion temperature is temperature at which a gas exhibits Joule-Thomson effect. What is Joule-Thomson effect? Joule-Thomson effect is when a gas is taken in a porous plug, when gas is subjected for adiabatic, when a gas is subjected for adiabatic expansion, when a gas is subjected for an adiabatic expansion, what is adiabatic expansion? Here it is, this is not only true for expansion, even for compression also the law is applicable, but whatever it is, let us see. When a gas is subjected for an adiabatic expansion reversibly, what is adiabatic? Adiabatic means the process is carried out at constant heat without changing the heat content. If the gas is allowed to expand, then there occurs sudden cooling. And on the other way, if a gas is subjected for adiabatic compression, adiabatic reversible compression, when a gas is subjected for an adiabatic reversible compression, then there occurs a sudden heating. So, occurrence of this sudden heating or cooling in the adiabatic expansion of a gas through a porous membrane, is what is called Joule-Thomson effect. This is what is the principle in fact that we use in the refrigerators. Refrigerators works on the principle, refrigerators, ACs and all, they will work on the principle of expansion of a gas and thereby decrease in temperature, that is cooling. When gas is allowed to expand in a mesh like arrangement, small narrow pipes that are given with the help of a that is what in fact we call compressor, where the gas is in a compressed state. From the compressed state the gas is allowed to expand through a mesh type arrangement. Through that mesh type pipes the gas is slowly expanded, that is reversible expansion, adiabatically, no exchange of heat, right. Then there will be a sudden change in the temperature, that is it suffers cooling effect. Because of the expansion, what happens is there will be decrease in the kinetic energy, as a result that brings sudden change in the temperature and cooling effect takes place. And in the adiabatic compression, as the molecules come with close intermolecular attractions, the molecules will come with close intermolecular attractions as they are coming, then in that case there occurs what happens is, due to compression there will be increase in temperature, that means the gas suffers heating effect. Now what is inversion temperature? The temperature at which exactly gas exhibits this Joule-Thomson effect. Sudden temperature at which there is a sudden cooling or heating effect takes place is what is called inversion temperature. For any gas, inversion temperature is equal to 2A by RB, that is the inversion temperature. For any given gas, the inversion temperature is determined as 2A by RB. For any gas we can determine. Now actually this Joule-Thomson effect application, what is adiabatic process, what is adiabatic reversible expansion, the significance and all this, it is in fact studied under the thermodynamics topic. But here as an application for the gaseous gases, it is necessary for us to discuss over here. So is the reason we are in brief discussed about this Joule-Thomson effect, that is the occurrence of sudden cooling or heating effects by a gas during adiabatic reversible expansion or compression, right. Now here the points what to remember are ideal gases, ideal gases do not exhibit Joule-Thomson cooling or heating effects. What is the reason? Ideal gases do not exhibit this Joule-Thomson heating or cooling effects. What is the reason? The reason is simple, because here the entire thing is based on the intermolecular interactions. In an ideal gas, intermolecular interactions are negligible. We do not consider the intermolecular interactions. Intermolecular interactions we consider only for real gases. And this term A, van der Waals constant A, of course refers to, or it is a measure of intermolecular attractions. So, where the intermolecular attractions are absent, no cooling or heating effects. That is reason in refrigerators, in the compressor the gas taken will be something like ammonia gases, of course not exactly ammonia, freons or their derivatives, ammonia derivatives. So, there are something that kind of gases which can be liquefied easily, they are the ones that are used. So, it is the gas will be taken in a compressed state. Also hydrogen and helium also do not exhibit Joule-Thomson effect. Hydrogen and helium also do not exhibit Joule-Thomson effect. What is the reason? Even though we do not consider them as ideal gases, but they are the two gases which always exhibit positive deviation. Their molecular size being very small, this is what already we discussed in the van der Waals equation. Their size being very small, the intermolecular attractions are negligible. In fact, for those gases repulsions will dominate attractions because of the size factor. So is the reason, and also we told the A value for hydrogen and helium is very less, right. Therefore, hydrogen and helium also do not exhibit this Joule-Thomson effect. Then gas with higher value of A and of course lower value of B. Gas with higher value of A exhibits more of Joule-Thomson effect. Gas with more value of A, gas with higher value of A. Gas with higher value of A is nothing but where intermolecular attractions are high, or the gas which can be liquefied easily liquefiable gases. Again example like ammonia. Ammonia is a gas which can be easily liquefied, liquid ammonia. Ammonia like gases with higher value of A which can be easily liquefiable, they will exhibit more of this Joule-Thomson effect. In fact, that is the reason ammonia is one of the refrigerating gases, but of course we have certain other problems with ammonia. So, normally it is not advised to use in a ammonia alone, but otherwise it will exhibit a very good Joule-Thomson effect, and it is one of the refrigerating gases, right. So, this is all overall now gives us a broad outlook on the topic of the gaseous state. With this we can conclude the topic of the gaseous state as far as the theory is concerned, and of course we have to do more numericals, different types of questions what likely to appear in the JEE mains as and advanced. But as far as theory is concerned, with this we can stop it. Thank you.